Okay, so hi everyone. Welcome to the IARCS verification seminar series, and we are happy to have Sumanth Prabhu giving the talk today. Sumanth works as a scientist in the Foundations of Computing group at TCS Research in Pune, and I think last year he completed his PhD. Last year, Sumanth, right?
Uh, this year, yeah. I mean,
This
it
year,
was
okay. Yeah.
December.
So
Yeah,
recently he
December
completed
years.
his
Right.
PhD from ISC working with Deepak. He broadly works in the area of formal verification, synthesis, and today he'll tell us about precondition inference for array programs. Yeah, Suman.
Thanks, Madhukar. Yes. So this work is on, like Madhukar said, weak-edge precondition inference for linear array programs. And the talk will be based on two papers which recently got published in ETABS. And this is a joint work with Deepak Gregory from Florida State University, Supratik and Venki from TCS Research. So let me begin with the problem of precondition inference. So we are given a program and a post condition. So the program can have one or more loops, and the post condition is expressed as an assert statement in the program itself. The problem is to find a set of initial states which can be considered as safe. That is, from those initial state, if you execute the program and if the program terminates, then whatever state that we get should satisfy the assert condition. That is, should be there in the post condition. So this is called the maximal. This is called the precondition, and maximal, such a maximal set of safe initial states is called the weakest precondition. And the problem is to automatically find such maximal or the weakest precondition. There are
Sumanth,
many
would you turn on
applications.
your video? Sorry,
Yeah.
I'm not able to see.
Okay. Let me just.
Oh,
Okay. Yeah. There are many applications of preconditions. One is once you find such preconditions, you can annotate these preconditions by the code where you have found this precondition. And this is useful in modular verification. Say you have a large piece of software and which is not possible to verify in one go. So you can kind of annotate some subpart of the program and then modularly verify them. So for these annotations, one can find preconditions for say functions or some piece of code and then annotate those code with these preconditions. Also, one can find preconditions and add them in the beginning of the function or the program so that only those input values that are allowed by preconditions are taken. Otherwise, maybe an exception can be raised so that only desirable input is given to the program. And also preconditions can be used in testing as well. Say you do whenever you do an integration testing where you verify a large piece of system or software, and you can kind of detect which piece of software is failing in testing by looking at which preconditions are violated. And precondition also gives precise documentation. So what is allowed for a program or a function and what is not allowed. Right? So there are many applications in software engineering, like I mentioned. So precondition inference is an important problem. At the same time, it is challenging to find preconditions for programs that have arrays. I will look at this small example where we have a function foo, and it is taking two arrays a and b. Arrays are unbounded, that is, they have the size n, but we do not know what is the value of n. N can be any value. Precondition can be considered as the as a function which is in the beginning of the this function that is getting called and initializing all the values of these variables a, b, and n. After this precondition call, there is a loop here. Now loop is in the loop, the value of a is getting updated by its own value and the corresponding value in b. Finally, once the loop terminates, there's a post condition that says that between 0 to n, the value of a is greater than the corresponding value in b. Okay. So you can, in this program, you can see some of the features of the program. First is for a given value of n, it is always terminating. So it always reach this assert statement. Then the arrays are accessed by this I here, which can be considered as a loop counter for in this loop, and also this I is getting monotonically increasing, right? So in each iteration, I is getting incremented by 1. And also the post condition is a quantified formula over arrays. Okay, so it's an implication. On the left hand side, it is giving some range of array index, and then on the right hand side, it is giving some constraint on array values. Okay, so these are what are known as what we call as linear array programs. I'll come to what these characteristics are. But let us look at some of the challenges in finding weakest precondition for such programs. So first is, once you find precondition, you have to prove that they are the weakest one. For instance, you can overly constrain a precondition. For instance, this n is 1 and a and b has some values, which is a precondition for this program. But you can see that many other values can also be allowed for this precondition. You can start with other values also and still satisfy this asset condition. So once you find a precondition, you have to prove that the weakest one, it is the weakest one, and weakest preconditions are useful in the applications that I mentioned earlier. Second is typically you have programs with the loops, and loops can be unbounded. For instance, here it depends on the value of n, and n value can be anything. So to reason about unbounded loop, you need to find one way is to find inductive invariants, and the current inductive invariant inference techniques that crucially depend on the given precondition. That is, given some precondition, it will find an inductive invariant, whereas in this case the precondition itself is missing. Then finally, as I mentioned, the post condition is quantified. The problem with quantified post condition or quantified formulas, there are multiple problems. So first is there can be a large search space of possible precondition, inductive invariant, and so on. And second is, of course, it's difficult to reason about quantified formulas. So existing solvers many times it becomes undecidable to even decide the satisfiability of quantified formulas over arrays. So overcoming these challenges, our technique finds the weakest precondition for this program, which is between 0 to n, a of j is greater than 0. Along with the weakest precondition, it also finds an inductive invariant, which is the proof of validity. That is, you can plug in this precondition and inductive invariant and then try to see that those are valid. And also, it also gives a proof of maximality that proves that this is the possible weakest precondition for this for what a given program. Okay, so I mentioned we target this linear array program. So this is, I'll just give a brief description of the properties of such linear array programs. So first is they are terminating programs, and then they can have multiple loops, but loops are non-nested. Array accesses are done using these counter variables, which are monotonically changing. It can increase or decrease, but they have to be monotonically changing. And then the post condition is is either universally quantified or existentially quantified. If it is universally quantified, it is an implication. Whereas on the antecedent, that is left hand side, it will be a range of values that the array index can have, or multiple array indices can have. And on the right hand side, it constrains the values that arrays can have. It will be an array formula. It's a formula over both array variables and integer variables, and constrains the values that arrays can have. Similarly, we can have an existentially quantified post condition, which will be a conjunction again over range and array formulas. Okay, and many of the existing array verification techniques target such post condition. So we also target such post condition in our linear array programs. So our first contribution is we prove that even though we have this syntactic
Sumanth, Madhukar
restriction.
here.
Yeah. Yes, Madhukar.
Yeah. So these are actually the same post conditions, is it? Negation of each other, something like that?
Oh, right. This is negation of this. Yeah, existential.
Okay, right. Sure. And when you say monotonically change, you mean that they just you don't go back to a previous index, or
right. I don't go back to a previous index.
Okay, sure.
Yes. Yeah.
So,
so
Sumanth,
yes.
so there is no
restriction on the kind of assignments you could make to the array elements?
Right. Assignments are linear assignments. I can have only linear assignments.
Oh, the assignments have to be linear too.
Right, right.
And
Linear. Yes.
what does array access counters monotonically change? What are access counters?
Right. So access counters are, say, for instance, you have some counters in the loop, and using those counters, only array accesses are done. For instance, I here, and those are monotonically changing.
So
Okay, they
every
have to be-
variable, no, I don't understand. So you suppose you can have expressions in place of the indices of the array access. Do you allow expressions there?
Yes, I allow expressions, but those are linear expressions. Only say, like say n minus I or I 2 times of I, such.
And every variable that is used in there should be monotonically increasing over
Yes,
the iteration of the loops.
Right, right. Yes, yes.
So linear expressions are allowed, but every
Linear.
variable, which is what you call
Yes.
array counters,
Right, right.
should be monotonically increasing.
Monotonically. Right, right.
Okay.
Okay, and more formal, yeah, more formal grammar and all is there in our papers, so you can refer them. So even though with this restriction, the weakest, I mean, the computing weakest precondition is still uncomputable. I mean, it's undecidable for such linear array loop programs. But at the same time, many of real-world programs can be represented by such linear array programs. And also existing array verification techniques target such class of programs, but they do array verification. That is, you have to give a precondition along with the program and post condition. They verify those 3 triple R valid. Okay, so we now target, can we find preconditions? So there is precondition is missing. Can we find preconditions for such programs? Okay, so we have 2 papers for this. So one is for deterministic program and another one is for non-deterministic program. And the main contributions are, first is of course the weakest precondition technique, which we do it in a framework that we call infer check weaken. So the idea is to find to infer a precondition, and then there is no constraint on the inference. It has to be just a valid precondition, and then check its maximality. And then if it is not maximal, weaken the precondition. And for deterministic program, we have a range abduction as an inference technique. And for non-deterministic, we have something called structural array abduction. And maximality checking also, we have 2 techniques. One we call complement checking, and another one we refer as specialized checking. This is for deterministic and non-deterministic respectively. And these have been implemented in 2 tools, MaxPrank and PreQSyn, which are available in public. And in the rest of the talk, I will give brief summary of these techniques. And I'll try to illustrate range abduction. Okay, so like I mentioned, we get these preconditions in infer check weaken framework. So the idea is first to given a precondition task to infer a precondition along with inductive invariance, which proves its validity. Okay, there is no constraint on, there is no hard constraint on infer that it has to find the weakest precondition. But you know, if you find weakest one, this is well and good, because once the precondition is found, that will be passed to the maximality checking. So maximality checker encodes a new problem, which is similar to the precondition inference problem. Depending on deterministic or non-deterministic, we encode different different problems. So the idea here is maximality checker again depends on the infer engine to solve this newly encoded problem. Okay, so that's why it is kind of near to the precondition inference problem. Now, inference, now depending on the result infer module returns, the maximality checker will decide whether the current precondition is the weakest one, or it passes the precondition to a weakening module, and the weakening module gives a weaker precondition, and then this loop continues till it finds the weakest precondition. So first I'll now cover deterministic programs. So first is infer module in deterministic program that we call as range abduction. So the idea of range abduction is to start with a candidate solution. The candidate solutions form will be again something similar to the post condition that we saw earlier. So one is universally quantified with range and array formulas and implication. And second is existentially quantified with range and array formula. And the candidate solutions can be a Boolean combination of these also. By candidate solution, what I mean is precondition along with inductive invariants or loop invariants for each of the loop that are there in the given program. Okay, so it starts with such a solution, and then using SMT solver, it tries to check whether these are indeed solution for, or rather precondition and inductive invariant for the given program. So we fix this form for this reason, that we are using SMT solver to check whether this particular whether the candidate solution is indeed a solution, because SMT solver, from our experience, scales or is able to solve our this checking of candidate solution when they are of these forms, so for all and their existential. If the SMT solver is not able to check, or gives that this is not a candidate, so this is not a solution to the given problem, then we try to improve the candidate solution by using strengthening or weakening. So the idea of strengthening is, can we find a stronger solution than the current we have by using something called abduction, and weakening is done by something called Houdini. So Houdini technique is existing technique. We just use it for array. So I'll not go into this. We'll now look at how do we do strengthening of solution, that is, we get stronger solution by using something called abduction. Let me just give brief background about abduction. So the problem of abduction is, we are given some premise. The premise is some formula over a set of variables, say y. So we are given some premise and also a conclusion, again another formula over a set of y variables y. Now the premise is not implying the conclusion. So now, can we find a hypothesis h over a set of variables x, where x is a subset of variables that are there in y, such that h and p together implies the conclusion? Okay, so h of x and p of y implies the given conclusion. Also, this implication should not be vacuously valid. Okay, so I should have at least one model that is there in h as well as p, right? I mean, h and p should not conflict with each other. Okay, so there should be at least one model in h of x and p of y. Just to give you an example, suppose say an array update is happening. A p of I is getting updated by a of I plus b of I. And this is my premise, and my conclusion is, suppose say a p of I is greater than b of I. Okay, I want this conclusion, and this is my premise. You can see that this does not imply, for instance, a of I can be some negative value and b of I is positive value. In that case, this may not hold. In which case, now can we find a hypothesis over only a, b, and I that together with this premise implies the conclusion? Okay, so one hypothesis is a of I is greater than 0, that together with this premise, we can see that a p of I will be greater than b of I. Okay, so this is some background on abduction. We'll see how we use this abduction technique later. Okay, so now going back to the example that we saw earlier. So we had a program. That program had precondition in the beginning, and there was a loop. Okay, so the loop had inductive invariant. Okay, so I mean, there is a loop. Now, suppose say we represent this loop's inductive invariant by this uninterpreted relation INV. Okay, so INV. So in any iteration, INV will be over in the beginning of iteration. Suppose say it will be over A, B, N, and I, which are the program variables that are accessible at this point.
So Sumanth,
yes.
So sorry, Madhukar here. I had a
Yes,
question.
Madhukar.
So when you said that it should not be vacuously true. So for instance, here if we set in the example on the next slide, if we set n is equal to 0, that is the kind of precondition that you are trying to get rid of by the vacuity check, or is that still allowed?
By the maximality check. So that is, if it is valid precondition, that is fine. But yeah, maximality check will make sure the n equal to 0 is not. It will fail for that maximality check. But at the same time, I'll come to that a bit. We try to, whenever we try to find this solution to abduction, we'll try to find the weakest possible solution, weakest possible hypothesis for it.
Okay.
So,
okay. So you discard n is equal to 0 because of not because of the vacuity,
right,
but because of the maximality.
because of the local maximality check.
Okay, sure.
Okay, but any other abduction solver can also be used here. Just that the maximality check later on will find out this particular precondition is not maximal. It will give some counterexample to maximality.
Sure. Thanks.
Okay, right. But in our range abduction, we kind of remove such we remove such solutions by finding the locally maximal, at least locally maximal solutions. Okay. So now going back to this example, we have this loop. Now this loop, suppose say we represent this loop's inductive invariant by say I and V. This I and V will be over all the variables that are accessible here. So A, B, and then I. And whenever there is some update happening inside loop, so we'll represent the updated variables by prime variables. Say for instance, here A is getting updated array A, so A prime. B and N remains same, so B and N can be same, and I will get updated. I will be gets updated by I prime. Okay, and then of course there is post condition and all that, right? So now suppose say we represent the precondition by another unimperative relation, say pre, which will be over this A B N, and inductive invariant, like I said, by this INV and relation. Now, for them to be valid, right? For them to be valid, or for them to represent the semantics of program, they have to satisfy these three constraints. So the first constraint says that you get some precondition, and together with the initial condition of the loop, this should imply the inductive invariant. And then this says this is saying the inductive invariance has to be inductive. So you start with any iteration of the loop with A, B, and I. And if you enter the loop, right? So if the loop guard satisfies, and you do the update that is happening, right? So that is A of I is getting updated by A of I plus B of I. Yeah, once the update happens, and I also gets incremented by 1. Now, whatever state that you reach, that should also be there in the inductive invariant. Okay, so this is the second clause. And the third clause says that whenever the loop exits, right? So whenever we exit the loop, the program exits the loop, whatever state that inductive invariant has, and this exit of loop, this should imply the post condition, the given post condition. Okay, so we are kind of symbolically representing this program using these three clauses. So these are called constrained horn clauses. Just that this goes left hand side on constrained horn clause. But if you are not aware of constrained clauses, it's okay. So I'll not go much into details of constrained horn clauses. Okay, but I hope this is clear. These constraints, and once you find some pre and INV, and if you substitute them in place of this pre and INV, and if those once you substitute, and if it makes each of this implication valid, then we have a valid solution, valid precondition and inductive invariant for the given program. Okay. So now I'll try to illustrate range abduction on the program. Okay, so like I said, we start with some candidate solution. So in this case, say we have started with the weakest possible solution, which is true, and we see that true is will not make the third constraint valid, right? So third implication valid. Okay, so you can see that true and I is greater than or equal to n does not imply this j is between n to a of j minus b of j. Okay, so now what it tries to find, now the range abduction, what it tries to do is, we have a post condition here which is quantified and all. So can we find a candidate? Can we assume or can we find a candidate solution from the post condition itself? Okay, so in the next iteration, it takes the post condition, but it strengthens the range of the post condition. Okay, so the idea here is the loop is monotonically increasing. So it is increasing from 0 to I. It has changed the values of arrays from 0 to I, and it is yet to change from I to n. So, so what has to happen is this, whatever the values that are there over array should hold over between 0 to I. Okay, so based on that, it will add this range that between 0 to j is between 0 to n, and also between j is less than I, which is 0 to I, j is between 0 to I. A of j is greater than b of j. Okay, so it will do this computation, how what variable is from what variable the arrays are getting accessed, and also how that variable is it getting monotonically increasing or it is monotonically decreasing. Based on that, it adds this range. Okay. Now, once it adds this range, this is a new candidate solution. Now, again, it checks. Again, it asks SMT solver to check, I mean, SMT checker to check whether this is a valid implication. And now the second constraint will not be valid. Okay, so you can see why, because there is constraint on 0 to I, but at ith position, right, we do not have any constraint on A of j being, any value can be there at A of I, right? So A of I is getting incremented by A of I plus B of I, but we do not have any constraint of A of I. So when I becomes, this I prime becomes I plus 1, then it will be less than I prime. This will be j is less than I prime, which includes the ith position as well. In which case, why should A of I be greater than B of I? Because we do not know what was the previous value of A of I, right? So now at this point, the range abduction tries to strengthen it. Okay? One way is, you can pose this as an abduction problem. You have this as conclusion, whatever the given candidate as conclusion, and this INV is the hypothesis that has to be found, and this being just the premise that is given. But then the current abduction engines do not support quantified formulas over arrays. Okay, so they do not support such formulas. So what we do is, instead of giving it as an abduction problem over quantified formulas over arrays, we reduce it into two abduction queries. So first query is over the change segment. Okay, so you can see that there are two segments that is happening. One is this between 0 to I, where nothing is getting changed, and at ith position and ith position to n, where the change is happening. Right, so you can kind of separate this array indices into two parts. One is between 0 to I and from I to n. Okay, so using that insight here, so we pose two abduction queries. So the first array abduction query will be for change segment. So here, can we find some hypothesis over A, B, and I, and we can also include n here. So A, B, I, n, such that whenever it changes based on the transition that is there in the loop, so A prime of I gets updated by A of I plus B of I, and B prime of I remains same, it implies the conclusion from the inductive invariant, right? So whatever the candidate inductive invariant is there, but over the changed variables, that is A prime and B prime of I, because invariant will be over A prime, and B prime we can consider B prime is equal to B of I. So A prime of I should be greater than B prime of I. Okay, so can we find such a hypothesis which together with this premise implies this conclusion? This is still also not possible for the existing abduction solver to solve. So what we do is we do some substitutions here. We substitute these array terms by new integer terms, and then pass this as an integer abduction query, which the existing solver can solve. And then we find the weakest solution for this hypothesis here, which can kind of remove such solutions, say n equal to 0 and so on. But it is not guaranteed to give the weakest solution. But anyway, coming back, once we get an integer solution, we'll again resubstitute back integer formulas by array formulas, and then we construct quantified formula. Okay. So the second part is array abduction for the constant segment, where nothing is, where something is not getting changed. So array A of I, A prime of I will remain same, and B prime of I will remain same. In this case, it will be a simple abduction formula. So a simple abduction query, we'll get A of I is greater than B of I here. Okay, so this is again changed into integer formulas and then passed to abduction solver, and then we get back whatever solver, and again the integer formulas are converted back to array formulas. Okay, so in this case we get two array formulas. So one is A of j is greater than 0 for the change segment, and second one is for unchanged segment we get A of j is greater than B of j. Okay, so this is now combined to get a quantified formula. In this case, the computation of range is done. So range is, like I said, 0 to I is where there's nothing is getting changed. So this j of less than I, we'll have the h2, which was not changed, right? So that array formula. And where the change is happening between I to n, j is greater than or equal to I, whatever the solution that we got, right, which is a of j is greater than 0, we'll add that into this. Okay, so we have constructed a new candidate solution. This passes, I mean, this makes the last two constraints valid now, except only the first constraint is there, which because we assume pre is also true in the beginning. So pre and I equal to 0 does not imply the given inductive invariant. Now, in this case, we can see that there is no, there's just one I equal to 0, but it could be the case that, this is not a precondition, but it is another inductive invariant for another loop. So we can have multiple loops also, right? So in that case, we have to, again, assume this is a new post condition and get a new candidate solution for this invariant and so on. But in this case, it is precondition itself. Is there a question?
Yeah. I mean, I was wondering, is this where, so the lifting from, by
Right.
splitting the two into the part that is change, not change, you lifted it into for all, okay?
Yeah.
So, I mean, this is where the monotonicity is used? I mean,
Right. This is where the monotonicity is used. Yes.
So it is not, yeah, that's crucial there. You can't just lift it.
Right.
Monotonicity.
Right. Yes. And if it's not monotonous, then we have to either change this range somehow, because anyway, this is just a candidate solution. We again ask SMT solver whether this is an inductive invariant or not. So, but then the range computation will be.
Yeah, I guess my question was in general. I mean, can you always lift it like this based on that two parts, one that doesn't change, the other one that changes? Is it always sound to?
What do you mean by sound? No, see, I'm trying to construct a new candidate solution.
You're saying that there is a universally quantified version, a formula that you're generating, and I.
Right.
Oh, but that. So, is it always sound to replace it with that universal quantification, like the way that you did?
Sound in what sense?
Is it true? I mean, is it always going to be true?
Is it always going to be true? No, it need not be an inductive invariant, because that is why we again check it.
You again check.
Yeah. So this is just a candidate solution. We are guessing candidate solution. This is a way to guess from an existing solution. We are trying to guess from an existing candidate solution. We are trying to improve.
So you just put the universal quantifier.
Yeah.
Okay.
Based on the post condition. If post condition is existential quantification, so we would have had an existential quantifier.
Oh, okay.
Yeah, it's based on post condition.
Oh, okay. See, because it is an existential quantification, that's where the universal quantification came.
Right. Okay, and for a precondition now, all I have to do is propagate this I equal to 0 in the existing this inductive, which I'll get this one. The range abduction finds between 0 to n, a of j is greater than 0. In this case, it is the weakest precondition, but we have not proved anywhere that this is the weakest precondition. So we need to do something called maximality checking. Okay, so now I'll cover maximality checking for deterministic programs. I'll try to give an intuition of how do we do maximality checking. So the problem is this: we have a precondition. So by definition of precondition, this is a set of states from which, if you execute the program, you will land in a state that is there in the post condition. Okay, so this is the definition of precondition that we have. Now, what is the problem that we are trying to find is there a state that is outside the precondition? Is there such a state that from where, if you execute the program, it will land into the post condition, right? If there is such a state, then the current precondition is not the weakest one, and this is a counterexample to maximality or CTM. Okay, if there are no such states that is outside the precondition, if there are no such states that always go into this post condition, then we prove that the current precondition is the maximal one or the weakest one. Okay? Or else, in other words, if I show that all the states that are outside the precondition goes to the negation of the post condition, then then it is proved that the current precondition is the weakest one. Okay? So this we can now pose this as a precondition inference problem also. Okay, so what we can do is we'll take with this, we'll consider the precondition, but for the negation of the post condition. Okay, so just we'll take the given program itself, but whatever given post condition, we'll negate it, and we'll try to find a precondition for that problem. Now that, suppose say we call that as C pre. Okay, in other words, say the given program that we had earlier, right? So that in the beginning, pre is replaced by a new precondition, let's say C pre, and the rest of the program remains same. And in post condition, we have negated that post condition. Okay, so this is where, say for instance, now we need to handle the existential quantification also. Okay, so now if we find a precondition for this, which I represent by C pre, just to make sure this is not conflicting with pre. So if we find a C pre for this program, then what we can do is we can check this, right? Is it the case that all the states that are outside the given precondition, which we have found earlier, if it is there in the C pre, okay, if all the states that are outside precondition, if they're in the C pre, then it is proved that this particular precondition is the weakest one. This can be, this validity check can be reduced to a SAT check. So is there a state that is outside the precondition and not of C pre, that is complement precondition? If there is such a state, then it is a counterexample to maximality. But we do not know, is it a counterexample to maximality for precondition, or is it a counterexample to maximality for C pre, that is complement precondition. Okay, so to find whether which of them it is, so what we can do is we can execute the program and execute it till it either reaches the negation of post condition or post condition. Like I mentioned earlier, we are assuming the programs are deterministic, so there will be a path. There will be only one path from the given initial state. So it will, if it either reaches the post or not post, then we will have a counterexample to maximality to either C pre or pre. Yes, now, depending on if we find such a counterexample to maximality, if there are no such counterexample to maximality, then it proves the current precondition is the weakest one. If we find such a counterexample to maximality, then weakening is done. So weakening is done using a syntax-guided fashion. So what it does is there is now we have determined by that execution whether pre or C pre is not maximal. That's one of them has to be weakened. And also there is a witness to non-maximality, which is that the model in not pre and not C pre. Right? Now, can we weaken the current solution to include the counterexample to maximality? What the weakening module does is it first constructs a candidate search space. So this can be given by the user, but what we do is we use some existing techniques to find this such a search space using syntax-guided synthesis. And also we are given this pre and C pre, and we know, which of them has to be weakened, and also this counterexample to maximality. And weakening will now find a candidate precondition and then ask this infer module, which range abduction, right? It asks range abduction to find an inductive invariant for the given candidate precondition. Okay, so infer, if it finds an inductive invariant, then by construction we have found a weaker precondition, and then that precondition is passed to maximality checking, and this loop continues. If it is not able to find, if it's not able to find a weaker precondition, I mean, it is not able to find an inductive invariant, then weaken will enumerate next candidate from this candidate search space, and this loop continues. Okay. So we have implemented this in a tool called Precondition, which is over our existing.
Sumanth, you go on. Sorry, I had a question. So you go adding this one by one, right? So you go on creating a disjunct and.
Yes. It is not just disjunction of CTM. So we kind of generalize this CTM to quantified formula. It will be disjunction of quantified formulas. It is not just a single CTM that we disjunct. Okay, so this candidate search space is done such that these are quantified formulas, which also includes this CTM.
Okay.
which user can give, or which we can consider. We find that for at least for the benchmarks that we had, we could automatically do this by existing.
Okay, sure. Thank you.
Okay. Yeah. So our tool takes CHCs as input. So CHCs constraint on clauses are like I showed those constraints. So those are like logical intermediate representation of input program. And we verified, we compared our tool against some 32 precondition benchmarks. So these were derived from the existing verification tasks. So we removed, so verification tasks that had multiple loops. So we removed the initialization loop and others, and then try to find precondition in place of them. So this is the result, just summary of result that we have. We compare it with PGen, an existing tool that can find quantified precondition for arrays. So our tool was able to find around precondition for around 97% of the benchmarks, and whereas PGen could find only for 6%. And our tool could prove weakest for around 90% of the time, whereas PGen was able to prove around 6% of the time. And the kind of preconditions that we got were mixed. So one in majority of the case they were maximal, and in 21 cases it was able to prove it is maximal. In 8 cases we manually checked that they were indeed maximal. In 2 cases they were not maximal. In 1 case it was not able to find the precondition. And also then we tried to check the kind of to see the difficulty of our benchmarks. What we did was we added these preconditions that our tool found, and we added them as the initial condition, and passed it to some of the state-of-the-art verification tools, and none of the tools could solve all the benchmarks that our tool was able to find preconditions along with inductive invariance. Okay, so now let us look at non-deterministic case, where so far we looked at the deterministic case. Now we look at non-deterministic case. This is another paper. So let's look at this program. It's a bit involved than the previous program. So what is happening is there are 3 arrays now. All are unbounded. They have n, but we do not know the value of n. Again, the precondition is there in the beginning. Now in the loop, the update is happening non-deterministically. Okay, so either C of I gets assigned to I, or A of I gets assigned to C of I. And then the post condition is there. Again, the post condition is quantified, where it is saying that A of j should be equal to B of j, no matter which path this program takes. Okay. Now, along with the difficulties that we saw earlier, right? So unbounded loop, weakest precondition, quantified post condition. Now there is this non-determinism also. Why non-determinism is difficult? So we will not be able to prove weakest precondition by using the previous maximality checking. For instance, you consider this. Suppose our technique found the infer module found this precondition. So this is the weakest precondition for this program. A of j, B of j, or C of j are all equal between 0 to n. Okay, now consider a counterexample to maximality that restricts n to 1, and A value is 0, B value is 0, and C value is say 7. Okay. Now depending on whether it goes to this if and or else branch, it satisfies the post as well as it satisfies the not post, right? So you can see that when it goes to if branch, then it satisfies this post. If it goes to else branch, it satisfies the not post, right? So we'll have a CTM which has path to both not post and post, which will not be able to use the previous maximality checking. Okay, so along with that, we also need a different infer module. So that is what we do. So I will not go into details of this. So this is what we refer as structural array abduction. You can refer the paper for more details. Very briefly, so what we do is we again do abduction, but instead of 2 abduction like we saw earlier, we have now some set of structural rules using which we'll have only one single abduction query. Using just one abduction query, we'll be able to get this quantified formula. Also, the range that we computed earlier using some static analysis, that range can be again computed by using these structural tools. Okay, and also along with finding inductive invariants and precondition, this structural array abduction can also find guards for this non-deterministic control flow. Okay, why do we need guards? So we'll look at maximality checking algorithm now. So now for maximality checking for non-deterministic programs, again, we have some precondition. Suppose say our structural array abduction has found a precondition. Okay, now, and also there is a post condition. Now the problem is there a state that is outside the precondition that has all executions, right? If you start from that state, all executions from that state should go to the post condition. And we are assuming this is a terminating program, so all executions will go to post or not post. So if you have a state, if it is outside the precondition and all executions go to post, then the current precondition is not the maximal one. If there are no such states, then the current precondition is the maximal one or the weakest one. Okay, so can we prove this one? Right, so let's look at slightly different problem. So is there a state that is there in the knot of pre, but those states have an execution that goes to not post, right? So you consider states that are not of pre, okay, and if it has at least one execution, if it has an execution that goes to not of post, then we cannot include such states. Okay, now if we prove that all states that are in not pre has an execution that goes to not post, then we prove that the current precondition is the maximum one, because all states that are outside it has an execution that goes to not post, so we cannot include any of those states in the existing one. Okay. So the insight that we have in this specialized maximality checking, that is the contribution that we have in the second paper, is that such executions can be represented by a specialized program or an under approximated program of the given program. Okay, so these executions can be represented by the input program, but it's specialized or it is under approximated. I'll illustrate this with the help of the previous example that we saw. Okay, so we had this precondition. So suppose say you consider not of pre, okay, which is not of this the given precondition, and you also consider the not of post. Okay. Now if I ask, if I give this to a verification engine, so I have pre and I have push, so I can give this to verification engine. Now it will not be able to prove that this particular program is either it's safe, right? So it will prove that this program is not safe, right? But why? Because we saw one CTM earlier that had an execution that goes to both post as well as not post. So there will be an execution here that goes to not of post here, right? So that goes to post here. Okay. So we'll not be able to use infer engine directly here. Okay. But now you consider this under approximated program. Okay, so here in this case, it has determinized this program, and since it has determinized, one of the execution which goes to post is now removed from this, but it is still an under approximation of the original program. Okay, so all the executions that are there here will be there in the given program also. So now now I can prove that not of pre and not of post for this program are valid. Okay, so not of pre program and not of post are valid. Okay, so that proves that all, and also this is a terminating program, so that proves that all executions from this not of pre for this under approximated program goes to not post, which also proves that not pre in the original program had an execution, at least one execution from each states of not pre goes to not post. Okay. What we find is the structural array abduction it's easier to find both this guard as well as proving that not pre and not post is a valid triple by finding an inductive invariant for this together, right? So these two can be found together. It gives okay, so there will be now new constraint, that is, can we find a guard such that that guard has an inductive invariant that together with that guard there is an inductive invariant for the given loop for the given not pre and not post. Okay, so this can be solved by the structural array abduction. This cannot be solved by range abduction, for instance. So this can be solved by a structural array abduction. So so the specialized maximality checking passes this problem to the structural array abduction, which is the infer engine, and depending on if it finds a solution, then the given precondition is the weakest one. If it is not able to find a solution, then it goes to weaken. But this is a slightly different weakening problem. We do not have a counterexample to maximality. Also, we do not know whether the given precondition is the weakest one or not. But what we try to do weakening similar to the previous one, just that the way we we construct this candidate search space is a bit different. So again, we construct this candidate search space with not of pre now. We do not have counter-exam manageability, so we consider not of pre and construct this candidate search space. And from this candidate search space, again, weaken will enumerate preconditions, and depending on the precondition, if infer finds a precondition, then if it finds an inductive invariant for the candidate precondition, then by construction it includes some states that are outside the precondition. So will decide that this is a weaker candidate precondition, this is a weaker precondition, and this will be passed to the maximality checking, and this will continue. Okay. If it is not able to find, then it goes to the next candidate from the search space, and this loop continues. Okay. So we have implemented these techniques, that is structural.
Sorry, there's a question. Yeah, so this guard. So I mean, how do you know if you found something which is too strong or too weak? How do you prevent yourself from
too strong or too weak forward? It will always be
So it's an under approximation.
Okay. Right. So I have not included that, but we make sure that whatever guards that we find, right, that also satisfies the semantics of if condition. That is, say I find some guard here, and say I have another else if here, and so on. So at least one of the if condition is enabled for any state. Okay, so that we'll add a meta constraint that one of the guard is at least enabled for each state. Okay, because earlier it was non-dead, so it was allowing it. So suppose
Sumanth,
this
could also be done by abduction. I mean, finding this guard.
Right. So finding this guard cannot be done by simple abduction, the abduction that I showed earlier. So because we'll have multiple hypotheses now, but it can be done using something called multi-abduction. Okay, so that is one extension that we do in structural array abduction. We solve it using something called multi-abduction. So there are multiple hypotheses that I need to find, which can be over different set of variables. Now, but these hypotheses together with the given premise should imply the conclusion. Okay, so this is called multi-abduction, and we solve it using this multi-abduction. Okay, so these techniques have been implemented in a tool called MaxPrank, which is again built on top of this HornSpec framework. So this framework is for specification synthesis given as constraint Horn clauses. And we evaluated over around 66 benchmarks, which had quantified post-condition. And we also compared this with, at least for preconditions, because the earlier tool, so none of the tools that we are aware can find this weakest preconditions for, we can prove this weakest precondition for non-deterministic program. For instance, pgen and prequizin, this is our earlier tool. This can only work on deterministic, and pgen can also work on deterministic programs. But at least they can find preconditions for non-deterministic programs. So we first compared with the number of preconditions that these tools can find. So our tool could find for all of them, and this can find 87% of them. pgen was not able to find any of the preconditions. And the number of weakest preconditions automatically proved, our tool was able to find around 90% of the time. It can automatically prove that the given precondition is the weakest one. Yes?
No, you said there were 66 benchmarks.
Right.
What was those? I mean, how did you choose?
These were right. So these were verification benchmarks, which had multiple loops. So we removed the initial loop so that in the initial loop.
What is so sacrosanct about these 66 benchmarks? I mean, they are like, I know you are getting 100%, okay, of these 66 benchmarks. Does it mean that you cracked the problem completely?
No.
When does your thing work and when does your thing doesn't work?
Right.
So I mean, you should have, at least can you give some idea of what these 66 benchmarks are? In what way is it representative of any program, array program that you could encounter or not, or what?
Some
intuition because you choose 66 and then you say 100%, you don't get an idea. Either we can assume that you have solved the whole problem and those
Right,
aren't
right.
being solved anymore, or there must be some restrictions now.
Yeah. Sure. Yeah. So restriction is, of course, a linear array loop programs, right? So linear array programs, those are the restriction. But these had linear array programs, and nested loop is also one restriction. But these
But
66
also with
benchmarks,
linear array
right.
programs, you
Yeah.
can come up with such complicated invariants. What is not clear to me is that I know that you have, I mean, what if you cannot, I mean, are there programs? I'm sure that there are programs where you, where your inductive invariants that you have, that you need to compute the weakest precondition, you may not be able to discover. No, there must be programs like that. It's because inductive invariant inference is an undecided problem. Or have you that? So then how can you get 100% unless you put some restriction?
No, 100% on these benchmarks. So these benchmarks are.
That's
so
what I'm saying. So there must be
Yeah.
something that is that you've exploited in these benchmarks that your technique is exploiting.
Right. So these benchmarks are from previous work, which where we chose multiple loop benchmarks from them, and they do multiple kind of array operations, say storing, copying across arrays, searching in arrays, and so on.
No, I understand. I think let me rephrase my question. It would have been more instructive if you had at least shown some benchmarks for which your technique fails and doesn't work.
Right. So these are linear array programs, right? So
no, I don't believe this. Even with linear arrays, you can solve the entire class of linear array programs. Such you can discover inductive invariants for the entire class of linear array programs.
That's not what I'm saying. Yeah, but at least on these benchmarks, which were their existing ones, we could solve.
Well, then my comment stands. I would like to see some, programs for which your method doesn't succeed.
So Sumanth, is it, I mean, maybe also as Madhukar was saying, right? If you just take n, can I take a trivial precondition, like n equal to 0?
Right.
And that will always be a valid, maybe I can also find a loop invariant for that. That will always be a valid precondition.
Right.
So maybe to answer Mandyam's question, it's not surprising that one can find some precondition.
No, that
for all these.
But there was, I mean, if you have.
So, I mean, what is interesting is we can find weak enough preconditions and, even ideally prove that they are the weakest. I think that's the challenging problem.
Yeah.
No, but the thing is, well, anyway, maybe you can take offline. But what if you cannot find you have to find an invariant also along the way to get the weakest precondition, huh?
Right. But I mean, if I have a trivial precondition like n equal to 0, then I think one could come up with a.
There always exists some precondition. Is that what you're saying?
Yeah. I mean, something like, essentially false.
Yeah, well, then it is not interesting. No, I mean, I don't know how many of these benchmarks. I'm assuming that these 66 benchmarks, when you solve 100%, they were not, if 90% of them were false.
Right. Yeah. No, using his technique, he gets fairly weak preconditions. Yeah. That's
okay. Good. Okay. Now I have the thing. Okay. Now I understand. So you could get pretty weak preconditions. Okay. And then you could claim that, okay, my tool works for 100%. So
actually,
kind of misleading.
I mean, I think you mean strong, but
yeah. Okay. Yeah. Yes.
I mean, the stronger it is, the less useful.
Yeah.
Okay. So, and our tool could prove around 90% of them to be weakest preconditions automatically, and then also we gave these gave these benchmarks along with the preconditions that our tool could find to some of the state-of-the-art inductive invariant inference engine. So, for instance, Freecon and Spacer, and none of them could find for all the benchmarks that our tool was able to find. Okay, so this is these are the two works that we have on weakest preconditions, and we target this linear array programs. And also, while finding weakest preconditions, we also give maximality proof, which is the under approximated program that we saw earlier, and also C-pre, which is the complement precondition, along with validity proof, that is loop invariance or inductive invariance. So you can access our papers here. So there are more details on the kind of benchmarks that we solve, and what are the limitations of a technique and so on in these papers. So you can look at these papers. So that's all I have. If you have any questions, I'll take them.
Yeah, thanks, Sumanth, for an excellent talk. Of course, I have some questions, but I will let others, if they have any questions, go first. Okay, so maybe I'll begin with one. So you talked about this the monotonicity condition on the post condition, right?
On the loop counter.
On the post condition, I think the post condition does not go back.
No, the loop counter is not. So loop counter is monotonically changing. Post condition is of
access
this
counter.
form.
Okay.
Right.
Okay. So there were. I mean, did you come across many programs? I mean, you can always craft one, but did you come across many programs and existing benchmarks where this was not there? So I just wanted to know how restrictive were these conditions that you had.
Right. So yeah, there are. At least we saw in SVComp, and SVComp typically had these monotonically changing benchmarks where I mean, say I gave a very simple example, but you can have, say, if condition with 2 times of I is less than n and so on. Different ways to do the update. Yeah, typically monotonically increasing, and this is not just us. Like I said, this is assumed in other array verification works also. This is assumed condition. So yeah, this is, but of course, like you said, yeah, you can always construct one. Say, for instance, break in between, right? So that is something which you not be able to handle. Say some I is some value, then you break something, right?
Yeah.
So that may not, yeah. So that is something which may not be.
And similarly about the post condition, I mean, did you find programs where you could not? I mean, which had different post conditions?
Right. Post condition is yeah. So we assume the post condition here, at least the quantified variables. Right? This is just for the range computation and all. We assume it is just a single variable. But for instance, sorting and all, you can have multiple variables.
Okay.
Where, I mean, we have to extend range for that, range computation for that. But at the same time, sorting typically require nested loops. Right? So that is, yeah. So that is one limitation that we have. So we can have multiple loops, but they are to be sequentially given loops. But nested loops is something where because of range, how do we compute those range, right? And also the shape of precondition and all can be different. It need not be the same as. It need not follow this particular format. So because of those two reasons, nested loop is something where which existing programs, or at least the existing benchmarks, typically are like say sorting, insertion sort, and so on.
Correct.
Yeah,
So
one
to
other,
find any precondition is I mean, weakest, of course, is difficult, but any precondition is also difficult for.
Any precondition is not that difficult.
Unless you get a trivial.
Right. Not trivial, but yeah, we can get non-trivial precondition.
How do you do that? You would.
Yeah, we have to extend this range to compute multiple. So we had this range computations. Here.
Okay.
Just a minute. This range computation. So now we, instead of just j, I need to consider one more for all j, k. How does this?
Correct.
How can I compute this range, new range to them?
Okay, sure.
Okay, so we have done earlier for nested loops. Just that here, this doing abduction and then adding it would, and also we're not able to get, say, for instance, sorting, right? So what is the precondition that we need there, right? So it is just true, right? So
True.
such a thing.
Yeah.
It's,
Okay. So we do have time for
Yeah.
a couple of questions. So if somebody.
right. If somebody has some.
Yeah. When I have a question,
Yeah.
Yes.
I know that these are, we call them linear programs. Sometimes, I don't know about the, you see, a lot of my questions are about because I don't understand what your restrictions are, okay?
Yeah, more
And,
formal
and
restrictions are there.
something, no,
in
let me finish
papers,
the question.
Yeah,
Okay,
yeah.
I know I can, not array programs, I can write some linear affine programs, okay?
Mhm.
Where the, although the program assignments, everything is linear,
Mhm.
but in order to actually prove with a precondition now, the inductive invariance could be what you might need will be non-linear. Okay, so
Yeah.
my question is about non-linearity. Now, I know
Mhm.
that you could, like Deepak mentioned, I mean, since you want to find some precondition that satisfies, firstly, your post conditions, you don't allow any non-linearity in your
No,
post condition, I'm assuming,
no.
correct?
Yes. No,
Okay.
no.
Now, even if you allow and use only linear in programs, sometimes in order to get a reasonable precondition,
Mhm.
you may need non-linear invariance. And of
Mhm.
course, you can make your precondition, you can get any precondition, something, maybe for that particular post-condition, you may need a non-linear inductive invariant.
Mhm.
Now, is that a restriction, or you can solve non-linear?
Yeah, that's a. It is not about us because see, in the end, we are using an SMT
No.
solver.
I don't. I'm just asking a question because I just don't know what
Oh
your
yeah, I'm
restrictions
answering.
are.
Yeah,
Okay.
yeah, yeah.
Yeah.
Yeah. See, it's this. There are two issues. One is, of course, so non-linearity. How do you find that you need a non-linear equation? That we can do it using abduction. For instance, abduction can give us some non-linear solutions, and that is the weakest possible solution. Then we can get it. But then, how do you prove it is an inductive invariant? Right. So typically, non-linear equations, right? So non-linear formulas difficult for SMT solvers to check, right? So
Why do
in
you
the
say
end, we
that?
are doing guess and check,
Non-linear, there are non-linear SMT
right? Over arrays, for array
over
expression,
reals. Okay, maybe not over integers and so on. Okay, yeah.
right? But for arrays, we need it for arrays, right? So in the end, we are checking whether quantified array formulas are inductive or not, right? So that is one bottleneck that we have, SMT checks.
So then what is your restriction then? I mean, you can come up with reasonable things. So
But I'll not be able to prove that that is a precondition.
then how will you be able to get a precondition?
Yeah, so we'll not be able to get the precondition then. Yes.
Okay, so with nonlinearity, there is
Yeah.
some restriction that you have.
Right.
All your
Non-linearity.
benchmarks, I presume that those 66 benchmarks did not involve such cases.
No, none of them, I think.
Okay.
Yeah. Yes. Right. So, yeah. So this is one, right? So, Kushal, we are dependent on this SMT check also, which is why we have chosen this particular format, which we find that SMT check is able to solve. SMT solvers are able to solve these formulas.
Okay. Anyone else? So, Suman, one of the things that I was,
Yeah.
how many iterations did you typically have to do to get to the weakest?
Yeah. So that's one interesting thing. So in most of the cases, we were able to find, I mean, the range abduction and structural array abduction was able to find, not here, but okay. So we were able to find weakest one, and just one iteration of maximal checking was we could prove that. But there were cases
Why
where
that was the case?
we needed weakening. So there's around 7 cases where we needed weakening. And the previously I showed one graph where, yeah, so this one, right? So 8 cases where in these 8 cases, in some of them we were not able to we were not able to get the C-pre and prove it is weakened. I mean, in these 2 cases, right? So in these 2 cases, we were not able to weaken it. We gave up after some time.
Okay.
So
You knew
there were cases.
and you knew that the
Sorry?
ones that you have are not the weakest.
I knew that. Yeah. Yes, we had some CTMs, and I was not able to. Yes.
Okay. So you give up after some iterations, or
Yeah, we gave up after some iterations. Yeah.
yeah. And any idea why
Because
you
this,
find the weakest ones very quickly?
because of abduction. So in abduction, we do the we try to find the weakest solution for abduction, right? So that helped us. That though it is locally this one, it gave us maximal precondition or the weakest precondition.
And the same holds
But
every
it is
time.
not always the case, of course.
Counter example. Every time you got a counter example, the counter example also had to be maximal in some sense, right? I mean,
No, not counter example. We didn't even get counter example. Say, for instance, in this case, we got both pre and C-pre to be this just one iteration. Both pre and C-pre we were able to get weakest one. So this query was unset. So there is no counter example. But in 7 cases we got counter example, but the weaken gave us candidate which was weaker than the current one, and which was also the weakest one. So I think we have gone some 3 or 4 iterations. After that, we are not able. We have given up.
okay. Sure.
Yeah.
Okay.
So the abduction is the one which helped us.
Yeah, certainly. Yeah. Okay, so if there are no further questions, let's thank Sumanth once again for a wonderful talk, and thanks Sumanth also for agreeing to
Thanks.
give a talk here. And yeah, I'll stop the recording.